Hey there, this is the first part 1 of the Anatomy of the Periodic Table lesson that's part of your chapter Elements and the Periodic Table. Before we can begin learning about the periodic table and the different parts of it and all of its trends, we need to understand a little bit about the atom. For the most part, you guys have learned this back in the 8th grade or IPC. But we haven't specifically discussed it yet. We will in a couple of chapters go into the atom models. But so let me give you a little bit of maybe a refresher with this primer, vocabulary primer. If you were to get just one piece of an element, just a single piece that still has all of the properties of that element, then you would have an atom. And if you were to look inside of an element that has a bunch of atoms, all of the atoms inside of that element are the same. Are they identical? Not exactly. But when I say that they're the same, that means they all have the same number of protons. Every single atom inside of an element has the same number of protons. And an atom is the smallest piece of an element that is still that element. Atoms are made up of 3 main things: protons, neutrons, and electrons. And you can see here that I have a little bit of shorthand that I use. A lot of people haven't seen these in high school chemistry, but it helps you out a lot in your notes if you start using them. For protons, you use a lowercase p with a little superscript plus sign. For neutrons, you use a lowercase n with a 0 superscript. And for electrons, you can see right there that you would use a little lowercase e with a negative sign superscript. Those, like I said, it helps you out so much to use those. Saves you time and space on your paper. The protons and the neutrons are located in the nucleus of the atom, right there. And the electrons are found outside of the nucleus, buzzing around in what we call electron shells or energy levels. It is way more complicated than that. We're going to get into it later, but it's even more complicated than what we'll get into later. But it is complicated. So if we look at this model of the electron or of the atom right here, you've got your nucleus that I've already pointed to that has the protons and the neutrons. Your electrons are buzzing around. Don't think of it so much as the solar system. A lot of people like to think of it as like, the nucleus is the sun with the planets orbiting, and the planets orbiting would be the electrons, but they're not in an orbit like that. So think of it a little bit more like maybe a wasp's nest, with the nucleus being the nest itself and the electrons being the wasps, or the buzzing around outside of it. So here, but the electrons are in energy levels, and we call them, for our purposes, we call them electron shells. So in this example that you can see to the left here, we have 2 energy levels, or 2 shells, and you have your inner shell right there, inner. And then you have your outermost shell right there. That's the one we care about, outermost shell. Boop. Okay. The valence electrons are they're special electrons. They're the ones that we actually care about in chemistry. Not that we don't care about the rest, but come on now. They're the ones that are found in the outermost shell of the atom. So there you have the arrow pointing to the outermost shell of the atom. The electrons in the outermost shell are valence electrons. They're all valence electrons in the outermost shell. So this atom has 4 valence electrons. I pointed at 1, 2, 3, and 4. It has 6 total electrons, 4 valence electrons. Please be careful in quizzes and tests and on your homework, because it's very important to understand and watch very closely. Are you being asked for the total number of electrons or for the number of valence electrons? Be very, very careful. And there I have pointed at an inner electron. Again, that's not a valence electron. Why are valence electrons so important? Well, it's because they are the ones involved in chemical reactions. So I can't stress to you how important it is to understand the difference between a valence electron and all the other electrons in an atom. If they're the ones involved in chemical reactions, and chemistry is the study of matter and the changes it undergoes, those changes are the chemical reactions. So you gotta know about the valence electrons. Please, if you ever, for the rest of the class this year, if you're ever forgetting what a valence electron is, please come back to this lecture, these notes, or just to me, and let's talk about it, because this is a fundamental subject that you need to understand. Now, do you need to understand it fully right now? You just need to understand the basics, because we're not going to be doing anything with the valence electrons here. All you really need to understand is just what it is and that it exists in order to understand the periodic table. And finally, one last note. This valence, you've been hearing me pronounce it valence. It is pronounced valence, and I'm just giving you a little bit of a clue in case you're not listening to me and you're just looking at your notes. Please put in there how to pronounce some of these words, because they are commonly mispronounced. If you're just reading, a lot of kids are pronouncing this valence, and that's not right. It is valence. Now we're going to look at ions. So more specifically, we're going to look at the electrons on the atoms. And this is a little bit of a primer to get you understanding ions. Atoms can gain or lose any of the three major parts that they have, protons, electrons, and or neutrons. Depending on which part they lost, we call them different names. Kind of like if they become a mutant, we have to name them so that everybody knows that they're a mutant, so that we know that they're not the same as what we see on the periodic table. The special name that we give them depends on what part of them changed, what part of them, I say mutated, just, because I'm thinking like comic book mutants, not biology mutants. So yeah, depending, so we know what changed on them. They have a special name that we can look at depending on what that is. Here's a note check for you. Do you remember what it is that we call atoms that have gained or lost protons? It's a little bit of a trick question, so put it in your notes and let me know what you come up with. We just kind of talked about if atoms lose or gain protons. Now, if they gain or lose neutrons, we do have a special name for them, but we're going to cover that when we talk about radioactivity, which is a really fun chapter, but we're just not going to cover it right now. Instead, we're going to talk about electrons. Atoms that have gained or lost electrons are called ions. Another way to say it is that atoms that have a different number of protons than electrons are ions. If you have more of positive than negative, or vice versa, more negative than positive, then you have an electrical charge. Now, is this the same as electrical charge? Yes, absolutely is. So next time you accidentally electrocute your father with the oven or stovetop, then yeah, thanks a lot, ions. That electrical charge can either be positive or negative. And just like we like to name the atoms, if they're different, then we like to give the ions special names based on whether they're positive or negative. The two types of ions are cations and anions, depending on whether they're positive or negative. First, we're going to look at cations. Cations are atoms that have a positive charge. They are ions, but they're a type of ion, and they have a positive charge. Because we're dealing with electrons and electrons are negative, when we talk about gaining and losing electrons and ions, whether they become positive or negative, we're totally in backwards world here. So if you are positive, that means you've lost one or more electrons. So just remember, it's kind of backwards. A lot of people get confused there. So gain or lose an electron, if you lose an electron, you become positive. Another way to look at that is to say that a cation has more protons, more positive, than it has electrons, negative. So it has an overall positive charge, a cation. An anion is an atom or an ion that has a negative charge. Remember, we're in backwards world here. So if you've become negative, that means you've gained one or more electrons. Again, another way to look at that is to say that it has more electrons than it has protons, more negative than it has positive. Alice and Lares came up with the best way to remember the difference between cations and anions, to remember that cations are positive and then anions are negative. And that is that cats, oops, that's not the right color. Here we go. Cats have paws. So cats have paws. And so cations are positive. Isn't that great? You can thank her for me. If you're interested in ions or you're totally not interested in ions, we have way more chapters later on in the book that covers this. So have fun with that. We're going to get way more into this. This is just an introduction. All right, why are the valence electrons so important? Because they're the ones that are involved in the chemical reactions. But why are the valence electrons involved in chemical reactions? The big reason is because of the octet rule. Basically, the octet rule says that atoms want to be stable. We all want to be stable, and they're most stable when they have a full outer shell, when valence electrons. So in order to get the full outer shell, in order to become as stable as they can possibly be, they hook up with other elements that also need to become stable so that they all feel like they have a full outer shell. Sometimes they share valence electrons with other elements. Sometimes they give away valence electrons, and sometimes they kind of, thieve them. They steal them from others, kind of. Those are all different forms of chemical reactions, and that is what causes chemistry, most of chemistry, and it's all because of the octet rule, and all because of the number of valence electrons. Usually, the outer shell of an atom is full when it has 8 valence electrons. That's why they call it the octet rule, octet for 8. But there are 2 big exceptions to that. We will get into those in later chapters, but I will tell you right now that if there's an exception to anything in chemistry, a lot of times hydrogen's involved, which is the case here. All right, we have learned this previously. Remember that on the periodic table, the rows going left to right, rows, you row your boat across the periodic table, we call those periods. Columns, Greek columns going up and down, we call those groups or families. And the elements are put in order. They're numerically, they go in that order, reading left to right. And then when you get to the end of the row, when you get to the end of the row, you go down to the next one and read left to right. Those are ordered by the number of protons they have. Then why is the periodic table shaped like that? Why isn't it one big square or rectangle? Well, the order of the elements comes from how many protons each one of them has, but they're organized based on how many valence electrons they have. In other words, they're grouped, they're put into groups based with other elements based on the number of valence electrons. So if, think of groups as in actual families or groups on the periodic table. They're in the same group with all the other elements that have the same number of valence electrons. So think about it. If the chemistry is happening because of the valence electrons, then it stands to reason that if you have the same number of valence electrons, you behave chemically the same way. This organization gives the periodic table its shape, that U shape, or I like to think of it as a canyon shape. And I already talked about this last bullet point, and this is why the elements in the same group have similar properties. They have the same number of valence electrons. That order and the organization, the order coming from protons, the organization coming from valence electrons, on the periodic table leads to trends that occur. Remember, the trends are occurring because they're grouped by valence electrons. So you start to see trends that occur as you move across the periodic table, and they repeat from period to period as you go across the periodic table. That is called periodicity. And we're going to get more into periodicity in the next chapter, so I'm not going to really talk about it right now. There are 2 major parts of the periodic table. The first part is called the main group, also known as the representative elements. And there I have circled the main group for you. We also call these group A elements, and we'll see why in just a few moments. These are called representative elements, and they're considered the main group because what I said earlier, the elements that are in the same groups have similar properties. They do follow that pattern. The second part of the periodic table, the second major part of the periodic table, are the transition elements. There are two parts to that, the transition elements and the inner transition elements. Here are the transition elements, also known as transition metals, and here are the inner transition elements or metals. Those two rows down there at the bottom. Those are all considered transition elements. And they're also called group B elements. And again, we'll see why here in just a moment. There are three different types of elements: metals, metalloids, and nonmetals. And here I already have a picture that has them pointed out to you. The nonmetals are the yellowish, goldish color. The metals, which we'll get into in just a moment, are the blue, and the metalloids are the purple. On the red thing down there, let me point at it, this red thing, we call that the stair step. And the metalloids hang out on the stair step. So if you ever hear me talk about that, that's what that is. Most periodic tables have the stair step is bolded so that you can see it. So what is a metal versus a non-metal versus what is a metalloid, right? So we need to understand the properties of a metal to understand what really a metal is, because a lot of people are really surprised at how many of our elements are metals. So metals are shiny, solid at room temperature, ductile, which means they can be stretched into wires. They are malleable, which means they can be hammered into sheets, or more commonly nowadays, they can be bent into shape or hammered into shapes. They are good conductors of heat and electricity, which that means a conductor allows heat and electricity to flow through it, as opposed to an insulator, which does not. And they, majority of metals, if you look at the stair step on the periodic table, all of the metals are found to the left of the metalloids on the periodic table. And here I have a picture of copper, a common metal that we find. And here I'm showing you all the different properties of metals with one element, copper. Here is the just regular old copper ore. You can see that it's shiny and it is solid at room temperature. Here I'm showing you that copper can be drawn out into wire. That's ductile. I don't know if I have enough room here. Ductile. And here I'm showing you that it's malleable. M-A-L-L-E-A-B-L-E. Malleable. It can be hammered out into sheets or hammered into different shapes. Here, these two, I'm showing you that metals, or copper specifically, is a good conductor. In this case right here, it's conducting electricity, and here it's a good conductor of heat. That brings us to the end of part one of this lecture. There will be at least one more part where I'll talk about a lot more of the periodic table specifically.